You've decided to fast. You've finished your last meal and the clock is now running. Most people who practice intermittent fasting think of this as simply not eating. But what is actually happening inside your body from this moment forward is one of the most sophisticated biological programs in all of human physiology. Over the next 16 hours, your liver will exhaust its glucose reserves and activate a completely different fuel system. Your fat cells will open their stores, your brain will shift its primary energy source, and at the molecular level, particularly between hours 12 and 16, your cells will begin a process of self-repair that is so important it won the Nobel Prize in Medicine. I'm a physician. What I'm about to describe is not wellness influencer content. This is the peer-reviewed biology of fasting, hour by hour, explained as clearly as I can. Let's start the clock. In the first 2 hours after your last meal, your body is still in a fed state. Blood glucose remains elevated. Insulin is circulating. Your cells, muscle, liver, and fat are absorbing the remaining glucose from that meal. GLUT4 transporters are still active, moving glucose from blood into storage. Nothing dramatic has happened yet, but something important is already beginning. As the last glucose molecules are cleared from your bloodstream, insulin levels start to fall. This falling insulin is the biological starting pistol for everything that follows. Think of insulin as a gate. When it's high, your body is in storage mode, building glycogen, storing fat, blocking fat release. When insulin falls, that gate opens. Your body begins its gradual transition from a fed state to a fasted state. Between hours 2 and 6, your digestive system has finished its work. There is no more glucose arriving from food. So, who is maintaining your blood sugar right now? Your liver. This process is called glycogenolysis, the breakdown of glycogen into glucose. Your liver was filled with glycogen from your last meal, approximately 100 grams, or roughly 400 calories, of rapidly accessible glucose. Now, under the instruction of glucagon, it begins releasing that glucose molecule by molecule to keep your blood sugar in the normal range. Your muscles also hold glycogen, 400 to 500 grams, but crucially, muscle glycogen is selfish. It cannot release glucose back into the bloodstream. Muscle glycogen exists exclusively to fuel muscle contractions. So the entire burden of maintaining blood glucose between meals falls on the liver alone. By hour 6, something important shifts. Insulin has fallen low enough to unlock a key enzyme inside your fat cells called hormone-sensitive lipase, or HSL. HSL is the molecular switch that allows your fat cells to begin releasing stored triglycerides. Here's the process. HSL breaks triglycerides into free fatty acids and glycerol. These free fatty acids are released from the fat cell into the bloodstream, where they bind to a protein called albumin, your body's fat transport vehicle, and travel to the liver and to muscle tissue to be burned as fuel. This process is called lipolysis, the liberation of stored fat. And this is the biological reality that most people trying to lose body fat are looking for. This is when your fat cells are actually opening, and it requires one thing above all else: low insulin. This is the direct connection to everything we discussed about blood pressure and insulin resistance. Chronically elevated insulin, driven by refined carbohydrates and frequent eating, keeps that fat cell gate locked around the clock. Fasting is one of the most powerful tools to lower that gate. By hour 10, your liver's glycogen reserves are significantly depleted. The tank that held 100 grams of glucose at the start of your fast is now critically low, perhaps 20 to 30 grams remaining. The body is becoming increasingly dependent on fatty acids as its primary fuel. Inside the liver, something new is beginning. As free fatty acids arrive from adipose tissue, the liver begins converting them into a different kind of fuel, ketone bodies. The primary ketone produced is beta-hydroxybutyrate, or BHB. At this stage, production is still modest, but it is beginning. At the same time, norepinephrine, a stimulating neurotransmitter and hormone, begins rising in the blood. This is not an accident. Norepinephrine is part of the fasting body's mobilization program. It enhances fat release from adipose tissue, increases metabolic rate slightly, and improves mental alertness. This is the biology behind the mental clarity many people report during a fast. It's not a placebo. It's norepinephrine. Hour 12. This is the moment that changes everything. If you remember only one thing from this video, remember this. Somewhere between hour 12 and hour 14, a fundamental metabolic switch is thrown. The term metabolic switch refers to the moment when the body's primary fuel supply shifts from glucose and liver glycogen to fat-derived ketones. This is not a gradual drift. In metabolic terms, it is a decisive transition. In the liver, beta-hydroxybutyrate is now being produced and released into circulation. Your brain, which normally relies almost exclusively on glucose, is beginning to receive a new fuel, BHB. And BHB is in many ways a superior fuel for the brain. It produces more ATP per unit of oxygen than glucose. It crosses the blood-brain barrier efficiently, and it acts directly on neurons to stimulate the production of BDNF, brain-derived neurotrophic factor, the protein that supports new neuron growth and synaptic plasticity. Hours 14 to 16 are scientifically the most remarkable window of a 16-hour fast. Two extraordinary processes are happening simultaneously: a massive surge in growth hormone and the awakening of autophagy. Let's start with growth hormone. During a fast of 12 to 16 hours, the pituitary gland increases its release of human growth hormone, or HGH. Studies show HGH can rise by 300 to 500% above baseline during fasting. The reason is elegant. HGH protects lean muscle mass during periods when food energy is unavailable. It drives fat burning while simultaneously preventing the body from breaking down muscle protein for fuel. This is one of the most important reasons why well-structured intermittent fasting does not cause muscle loss and may actually preserve it better than continuous caloric restriction. Now for autophagy. The word means self-eating in Greek, and while that sounds alarming, it is one of the most protective processes in all of biology. Autophagy is your cell's own internal recycling and quality control system. When it activates, specialized structures called autophagosomes, think of them as cellular garbage collectors, identify and engulf damaged proteins, dysfunctional mitochondria, and cellular debris. This material is then broken down and recycled into fresh building blocks. Autophagy is suppressed by mTOR, the cell's nutrient-sensing growth signal. mTOR is activated by food, particularly protein and glucose. When you fast, mTOR falls, and when mTOR falls, the autophagy pathway is released from suppression. Meaningful autophagy activity begins to emerge around hours 12 to 16, with the most robust activation occurring beyond 24 hours. But what is remarkable about the 16-hour fasting window is that you are genuinely beginning to access this repair system every single day, simply by extending your overnight fast. Let's step back and see the 16 hours as a complete biological story. Hours 0 to 2, the fed state clears, insulin falls, the fast begins in earnest. Hours 2 to 6, the liver takes over blood glucose management through glycogenolysis. Hours 6 to 10, insulin is low enough for hormone-sensitive lipase to open the fat cells. Lipolysis begins. Free fatty acids enter circulation. The body transitions towards fat as its primary fuel. Hours 10 to 12, liver glycogen is critically depleted. Ketone production begins. Norepinephrine rises, driving alertness and accelerating fat mobilization. Hours 14 to 12, the metabolic switch is thrown. Fat-derived ketones become the dominant fuel. BDNF rises. Brain clarity improves. Hours 14 to 16, growth hormone surges 3 to 5-fold, protecting muscle mass. Autophagy begins to stir, the cell's repair program activating for the first time. So, how do you access these benefits? 3 practical, evidence-based strategies. Strategy 1. The simplest 16-hour fast is an overnight fast extended by a few hours. If you finish dinner at 8 p.m. and delay breakfast until noon, you have completed a 16-hour fast entirely around your sleep window. No willpower required during the hours you're unconscious. Strategy 2. Break your fast with protein and fat first, not carbohydrates. Entering the fed state with a protein-rich meal, such as eggs, fish, or Greek yogurt, helps extend the insulin-lowered state slightly. It maximizes muscle protein synthesis following the growth hormone surge and avoids the sharp glucose spike that would immediately halt fat oxidation and ketosis. Strategy 3. Move before you break your fast. Even a 20-minute walk during the final 2 hours of your fast, around hour 14 or 15, can dramatically increase fat oxidation, extend the beta-hydroxybutyrate window, and activate GLUT4 transporters in a way that makes your cells more insulin-sensitive for the entire day. In other words, you are combining 2 of the most powerful metabolic interventions at the same time. Your body contains a biological upgrade program. It was written into your cells millions of years ago for exactly this purpose: periods without food followed by periods of abundance. Modern eating patterns have largely disabled this system. A 16-hour fast simply gives your body the opportunity to run it again. If this changed how you think about what is happening inside your body during a fast, subscribe to this channel for more science-based explanations of how metabolism really works. In the next video, we will explore the biology of what happens when you break a fast and why the first meal after a 16-hour fasting window may be the most metabolically important meal of your day. I will see you there.